Lecture 1, Introduction to Offshore Technology and Well Completion. Offshore technology is a critical field in petroleum engineering that deals with the exploration and production of hydrocarbons beneath the ocean floor. Offshore operations demand cutting-edge techniques, robust safety measures, and specialized equipment due to the complex and often harsh marine environment. Let us begin with well completion and safety techniques, which are essential phases in drilling and production. 1.1 What is well completion? Well completion is the process of preparing a drilled well for the production of oil or gas. It begins after the well has been successfully drilled to the target depth. Well completion involves installing casing and cementing, running production tubing, placing wellhead equipment, installing safety valves and packers, performing stimulation operations if required. 1.2 Safety techniques in drilling and completion. Offshore drilling comes with numerous safety challenges, such as high-pressure zones, blowout risks, and equipment failure. Common safety techniques include blowout preventers, BOPs devices that prevent uncontrolled release of oil or gas. Mud logging and monitoring, real-time observation of mud flow, gas influx, and kick detection. Kick tolerance analysis, ensuring that the well can handle unexpected pressure without a blowout. Casing pressure testing. Well control drills. Permit to work systems. Crew safety training and emergency response. Strict adherence to industry regulations and standards, e.g., API, ISO, OGP, ensures safety in every stage of offshore drilling and completion. Lecture 2, Offshore Drilling, Introduction, Challenges, and Key Concepts. 2.1 What is offshore drilling? Offshore drilling refers to drilling oil and gas wells in oceanic or sea environments, usually on the continental shelf or deeper waters. This is done using various mobile or fixed platforms, depending on the depth and environmental conditions. 2.2 Challenges in offshore drilling. Offshore operations are more expensive and technically demanding than onshore operations due to high water depths, strong ocean currents, wave action and windstorms, limited accessibility, storage and transportation logistics, environmental constraints and regulation. Lecture 3, Storage and transportation problems in offshore environments. Once hydrocarbons are extracted, they must be stored and transported safely to shore. 3.1 Storage issues. Limited space on offshore platforms. Requirements for high-integrity storage tanks. Environmental safety concerns regarding leaks and spills. 3.2 Transportation issues. Pipeline transportation, costly to install and maintain, vulnerable to corrosion. Shuttle tankers, a flexible but weather-dependent solution. Loading operations require coordination, dynamic positioning, and mooring. Operators must implement fail-safe systems such as leak detection, pressure monitoring, and real-time surveillance to minimize risks. Lecture 4, Prediction of wind, wave, and current forces. The offshore environment is highly dynamic. Predicting environmental loads is vital for design, safety, and operation. 4.1 Wind forces. Wind affects both surface equipment and floating structures. Parameters include wind speed and direction, turbulence intensity, seasonal variations. 4.2 Wave forces. Ocean waves exert cyclic loads on structures. Types include wind-generated waves, swell waves from distant storms, tsunami waves, rare but devastating. Wave models, e.g., Erie, Stokes, help in predicting their behavior. 4.3 Current forces. Ocean currents can originate from tides, thermohaline circulation, storm surges. These forces impact risers, mooring systems, and subsea cables. Advanced tools such as computational fluid dynamics, CFD, and oceanographic simulators are used to predict and mitigate these dynamic forces. Lecture 5, Types of offshore drilling rigs. Offshore rigs are classified based on their mobility, water depth capability, and function. 5.1 Jackup rigs. Used in shallow waters, up to 400 feet. Rest on sea floor using legs. Stable and widely used. 5.2 Semi-submersible rigs. Float on pontoons submerged below the waterline. Anchored or dynamically positioned. Suitable for mid-depth, up to 3,000 feet. 5.3 Drill ships. Modified ships with drilling equipment. Suitable for ultra-deep water, up to 10,000 feet. Equipped with dynamic positioning systems. 5.4 Fixed platforms. Permanent steel or concrete structures. Installed on the seabed. Used in well-established fields. Each type is chosen based on cost, environmental conditions, and water depth. Lecture 6, the operational environment, stability and motion. Floating offshore structures are affected by 6 degrees of motion. Surge, sway, heave, translational. Roll, pitch, yaw, rotational. 6.1 Stability. A vessel is stable if it returns to equilibrium after disturbance. Stability depends on center of gravity, buoyancy, ballast control. 6.2 Motion compensation. To ensure safe and accurate drilling, motion compensation systems are installed to minimize the impact of wave-induced movements. Lecture 7, Spread mooring systems and dynamic positioning. 7.1 Spread mooring systems. Use anchors and mooring lines to hold a vessel in place. Commonly used for semi-submersibles and FPSOs. Designed to handle multidirectional environmental forces. 7.2 Dynamic positioning, DP. Computer-controlled system that uses thrusters to maintain vessel position. Inputs from GPS, wind sensors, gyroscopes. Used in deep water where mooring is impractical. DP allows continuous drilling and production even in challenging sea conditions. Lecture 8, Offshore drilling rig equipment. 8.1 Rig floor equipment. Derrick/mast, structure that supports the drill string. Drawworks, controls raising/lowering of drill string. Rotary table/top drive, rotates the drill string. Mud pumps, circulate drilling fluid. 8.2 Motion compensation and marine riser systems. Heave compensators, offset vertical movements. Marine risers, connect seabed BOP to surface. Must be flexible yet strong. 8.3 Subsea wellhead and BOP systems. Wellhead, pressure-containing structure on the seabed. BOP stack, installed on wellhead to control pressure. Can be activated remotely. BOPs are essential for well control and blowout prevention. Module 1 Summary. In this module, we covered 1. The basics of offshore drilling and well completion. 2. Safety techniques and challenges unique to offshore operations. 3. Problems related to storage and transportation at sea. 4. Prediction and mitigation of wind, wave, and current forces. 5. Types and features of offshore drilling rigs. 6. Stability, motion compensation, and dynamic positioning systems. 7. Essential drilling equipment and subsea systems.